Hello, friends, and welcome back to the series on design of open channel flow. And today we are going to start with the third module, and in that first lecture is critical flow. So we have already studied the basics of open channel flow, the uniform flow concepts, and the design as well. And now we are going to study about the critical flow. So there is an extension of all the earlier concepts which we have studied. So our learning objectives are we'll be defining the specific energy and we'll explore its variation with depth, velocity and discharge. We'll understand what are alternate depths and critical depths. We'll also analyze how the flow can be categorized based on the Froude number, and we'll finally understand the concept of specific force. So the specific energy, that term, some you might have some resonance to it. So energy, you know that energy is whatever the work done, and in terms of fluid mechanics and hydraulics, the total energy is defined as the summation of the potential energy, the flow energy and the kinetic energy. So there are these three terms to it. Now for open channel flow, we make some modification, that is modifications to the existing Bernoulli's theorem, and we come up with this equation. Now, if the channel slope is very small, your cos theta becomes 0. And if it is a very small and straight reach and a prismatic channel, so your alpha will can be taken as unity. Now, if your datum that coincides with the channel bed, your z will become 0, and thus the equation reduces to E is equal to y plus v square by 2g. So this equation has two main components. One is the depth of flow and second is your velocity head. And the capital E, that is called the specific energy. So if we analyze this equation, so it is the total head measured with respect to the channel bottom, because your Z is equal to 0. So specific energy is the total head measured above the channel bottom. Alternatively, if we see that it can also be defined as energy per unit weight of fluid at any section measured with respect to the channel bottom. So that is what the specific energy can be defined. Now we know the continued equation Q is equal to AV. So here we are substituting V as Q by A. So our equation becomes E is equal to Y plus Q square upon 2G A square. Now your area, that is a function of flow depth. Okay, so essentially if you see that your specific energy has two terms involving flow depth, so specific energy again is a function of flow depth for a given value of discharge. So if your discharge is constant, your specific energy essentially depends on flow depth. Now this brings us to our question, that what are the dimensions of specific energy? Let us say you come out with the dimensions and you have to justify. If the dimensions are something unrealistic, then why so? Okay, because we are talking about energy. Now based on that, let us move ahead and understand what is the specific energy curve. So taking back from the equation 3 where we stated E is equal to y plus q square by 2g b square y square. So this is nothing but your area. Now Q by B, that is small q, that is discharge per unit weight, that we have seen earlier. So this equation can be modified as E is equal to y plus q square by 2g y square. So if we rearrange this equation, this y square here becomes y cube. So this has a cubic roots. So this equation has a cubic root. So it is an equation of a cubic parabola. So the three roots, when we solve it, we get two positive and one negative root. So this negative root you will be discarding, and these two positive roots, so you will get two values of y, and these are called alternate depths. So from this equation we can see that two positive roots are obtained for a given value of E at a particular discharge, so that there will be two depths which will maintain for a same specific energy. Now how can these two depths be maintained? So let us understand with the help of the specific energy curve. So if we draw a curve of specific energy versus the depth, we get this kind of variation. So let us understand that. So this is your specific energy curve. So this curve, this is your specific energy curve. So this is a given channel cross section. We take a small elementary width dy. This is your flow depth y. This is the top width. This is a area of flow. So when we plot, so let us say this is the equation of E is equal to y plus v square by 2g. So you can take depth increment. Let us say starting from 0 to 10, you take different depth increment. You have a constant discharge. Using this equation, you will try to compute the specific energy. So this yellow highlighted curve, that is curve A, C and B, that is the curve you get when you plot your depth versus specific energy for a given discharge. Okay, so here your discharge Q is equal to constant. Now, what we can see that this curve has two limbs. One limb is CB and second limb is CA. So this CB limb is rising upwards and it is asymptotic to a line drawn at 45-degree, that is line OS. So it is asymptotic. It will never touch that line, but it will be very close to that line. Similarly, the other limb CA, that is uh, gradually declining and it will be asymptotic to the horizontal axis. Now remember, this 45-degree line is valid for a channel of zero or small slope only. Then only this intercept will be at 45-degree. Now let us understand the role of specific energy. So we take any arbitrary specific energy E1. So we mark that specific energy ordinate as a vertical ordinate here. So this is a ordinate. Now it cuts the specific energy at 2 points. One point is R dash, second point is R. So at this point R dash, you the specific energy or curve, so the specific energy at R dash and R are same. Now this cuts the intercept at y as at y2 and here at y1. So you can see that for a given specific energy, there are two depths which are available. They are y1 and y2. So that is what we saw from the above equation where you got two positive roots. Now these two depths are called alternate depths. So this y1 and y2 are called alternate depths. That means for a given specific energy, for constant discharge, two depths are possible. They are called the alternate depths. Now let us take another condition where we are going to increase the specific energy. So specific energy, let us say I increase it to E2 at this point. So what is happening? The difference between my alternate depth is going on increasing. So y2 minus y1 is going on increasing with the increase in the specific energy. So if I take another section here, so you can see that this difference is going on increasing. Now let us move on the other side. So we'll move on the left side. If I take this section here, it is decreasing. Again, it is decreasing. Again, so there comes a point here where your y2 minus y1 becomes 0. That means, or they become equal, y2 becomes equal to y1. So there exists only one depth at a given discharge for which the specific energy is minimum. So this EC is a minimum specific energy and that particular depth is called the critical depth. So critical depth is a minimum is a depth at which your specific energy is minimum. Okay, now how do we characterize this alternate depths y1 and y2? So y2, you can see the depth is more, so it is a depth with a higher stage and lower velocity, because specific energy is a combination of two terms, depth and velocity. So if one term is high, the other term has to be lower because your E is constant. So your y2 is for higher stage and lower velocity, and y1 it is at lower stage and higher velocity. So this is the specific energy curve. Now what are our observations? So to summarize them, so for a given discharge, as E increases, the y2 y1, that is the difference between the alternate depths, increases, and E decreases, the difference decreases. Now, as we further decrease the E, your Y2Y, Y1 becomes 0. So, such that only one depth exists, and that particular depth is called the critical depth. Now, if you for critical depth, you have the minimum specific energy. Now, understand a specific energy which is less than the critical depth. Now, for this, there is no value of y that is possible, and flow cannot occur under such conditions. So, if you look at the curve as well, so if I take any value of specific energy which is lower than this, there is no value of depth which is possible because your curve doesn't go to that point. So that means there is no value of depth which is possible for E less than EC, and that flow cannot sustain. So to sustain that flow, you have to make some modifications, but for the given conditions, the flow cannot sustain. Now the condition where your specific energy is minimum, that is called the critical flow condition. That is very important, and we categorize it as a critical flow condition. Okay, now let us understand about the alternate depths. So in laboratory experiments, you have seen that there is a gate which is controlling the flow. So that is called a sluice gate. So it essentially obstructs the flow such that on the upstream you have subcritical flow condition, and the downstream you have supercritical. What are subcritical, supercritical? We'll understand in the later part of the lecture. So you have two depths. So the notations are just reversed. So this is y2 and this is y1. Okay. So these are the alternate depth, and this is a specific energy curve. Now, with the continuity equation, you have Q is equal to, that is small q is equal to V1 Y1, and that is V2 Y2. So if we apply the specific energy equation at two sections, section 1 and 2, so you get Q square upon 2G Y1 square plus Y1, that is equal to Q square upon 2G Y2 square plus Y2. So if you solve this equation, you will get your Y1 and Y2, and that is how your alternate depths can be obtained. Now, we come to a question that we discussed that in the specific energy curve, the line OS is at 45 degree for a channel of small or zero slope. Now, the inclination of that line will be different from 45 degree for a channel of large slope. Why? So the question is, why that will happen when the channel is of large slope? Why that angle will not be equal to 45 degree? So I'll give you a hint that think about the very first equation where you have the total energy, and understand that for, because we have already discussed in case of velocity distribution also, that channel of steep slope, how that velocity distribution component changes. So that is your hint to think about that answer. So moving ahead, we'll try to establish a criterion for critical state of flow. So we got that for critical state your specific energy is minimum. So how that criterion is established? So here we consider the specific energy for varying discharge. Now you must understand that, let us have this ordinate P dash. So the specific energy is E1, that is constant. So when we visualize it, that we discuss that the stage is high. So you can see that ordinate y2 is greater, and this ordinate v2 square by 2g, this is very small. So that is, for this alternate depth, the stage is high and velocity is low. Coming to y1, the stage is low, but you can see the v2 square, v1 square by 2g, this component is very high. So here the velocity is very high. So for a given curve, you get the critical point C, and like that, if you have so many discharge, let us say this lower curve is a discharge Q1. As you move in this direction, your discharge is increasing. So you have Q2 greater than Q1 and so on. So for each curve, you will have a critical depth or point corresponding to that, that is point C. So this dashed line denotes the locus of points joining all those critical depths. So this solid line at 45 degree is a line where E is equal to y, and this line is equal to E is equal to 3 by 2y. So that is the relationship between your depth and the specific energy. So that is your critical depth. So at critical depth, your Froude number, that is 1. So that state of flow is critical flow. Any value of flow where your Froude number is less than 1, that is called subcritical flow. And for Froude number greater than 1, that is called the supercritical flow. Now, this Q is equal to Qm, that is the maximum discharge that can be passed in the channel while you maintain your depth E1. Maintain the specific energy E1. So when specific energy E1 is maintained, that is a maximum discharge. So the critical condition apparently is a condition of maximum discharge as well. So the condition of minimum specific energy, but the condition of maximum discharge as well. Okay, so at critical depth, the specific energy is minimum. So we'll differentiate the equation 3 with respect to y and equate it to 0. So d by dy, so that is d by dy of y plus q square by 2g a square, that is equal to 0. So you get after differentiation d by dy, that is 1 minus q square upon 2g a cube into dA by dy, that is 0. What is dA by dy? That is the top width. So modifying this equation, 1 minus q square t upon ga cube is 0. So that becomes q square tc upon gac cube, that is equal to 1, or q square by g is equal to ac cube by tc. So this is the basic governing equation for critical flow conditions in the open channel, and the suffix c, that subscript c, denotes the critical flow conditions. So if you want to analyze a critical flow condition, this criteria should satisfy. Moving ahead, let us have two discussion questions based on this criteria for specification of the critical flow. That there are two open channels. One is laid to a slope of 1 in 5,000 and another is laid to a slope of 1 in 50. So one is a flatter slope, another is a steeper slope. So which channel would have the highest critical depth? That you have to answer, other factors remaining constant. Another question, that if I change the roughness of one channel as a higher roughness, one channel as a lower roughness, which channel will have the highest critical depth? So that these are the two questions which you need to answer. Now we know that the continued equation Q is equal to AV. So our equation 4 for the critical depth changes as this. Instead of Q, I'll have A into V. So that is V square T upon GA is equal to 1. Now this T I'm bringing down, so it is V square upon G A by T is equal to 1. Now what is A by T? A by T is D, the hydraulic depth. So your equation becomes V upon under root GD. Now this is the equation for Froude number, that is equal to 1. So for critical flow, your Froude number should be unity. So that is the necessary condition for the critical flow. Now for critical flow, your y is equal to yc and your f is equal to fc. So the equation is rewritten as q square tc upon gac cube is equal to v square c upon gdc, that is equal to 1, that is equal to fc. That is the Froude number at critical flow. So with the help of this, we can understand the types of flow based on the Froude number. So if the Froude number is greater than 1, then it is a supercritical flow, and if the Froude number is less than 1, it is a subcritical flow, and Froude number 1, it is a critical flow. So when the flow is supercritical, your depth will be less than the critical depth and the velocity will be greater than the critical velocity. For subcritical flow, it is opposite. Your depth will be greater than the critical depth and the velocity will be less than the critical velocity. And for the critical flow, your depth is critical depth and velocity is critical velocity. So let us understand where this practically occurs in a field. So I am showing a view where the river is being obstructed by a dam, then it is flowing over a spillway and again joining the downstream river. So this is the flow which is coming, it is flowing over the spillway and then it is again joining. So when flowing over the spillway, your velocity is very high and here your flow depth is very less. and this portion will characterize as supercritical flow. When again in the downstream, what happens? Your flow depth is high and the velocity is low, so it is a subcritical zone. Now in between the supercritical and subcritical, there is a transition, and somewhere in this zone the critical conditions will occur, and this transition from supercritical to subcritical flow is called as hydraulic jump. Okay, so it is called as hydraulic jump, where your flow state transforms from a supercritical to a subcritical state. Now let us understand how these variations in subcritical and supercritical flow propagate. So let us assume that an observer is sitting on the bank of a river, and we assume it to be a prismatic section and a rectangular section having flow depth y. So a river can potentially have three flow conditions with three different velocities. The observer is stationary, so the velocity v1 is less than v2, which is the critical velocity, and which is less than the velocity v3. So these three conditions are possible. So since the velocity is very high, v1, that case we will discuss first, and then we will discuss the critical and the supercritical stage. So now what happens? So at time t0, the observer throws a stone in the center of the river. Now when you throw a stone in a water body, the waves will be formed, and this like ripples will propagate. So let us say at time t equal to t star, the ripples propagate, which have a velocity g under root gy, that is a velocity of wave propagation, and the distance traveled, that is equal to under root gy into t star. Now what the observer sees, that the wave propagation travels upstream, that the distance traveled upstream is faster than the center of the ripple it travels downstream. So the to the observer it appears that the ripples are propagating upstream in case where your velocity is v1. Now let us go to the case where your velocity is v3, that is the highest velocity. So the ripples, they are propagating downstream at a higher velocity as compared to the center of the ripple, which is appearing to move upstream. So the movement of the ripples in the downstream direction is at a faster rate. So to the observer, the ripples appear to propagate downstream. And in the third case, where your velocity is v2, the movement of the ripples in the upstream and downstream direction are equal, that is the distance traveled is equal. So the ripple appear to be kind of stationary or traveling equally. So what these cases mean? So in the first case where velocity is less, so in that case your ripple, so any disturbance that is made in the flowing water, that would travel upstream when your flow is subcritical. When your flow is supercritical, any disturbances that are made in the water body would propagate downstream. So that is how one can potentially understand whether the flow is supercritical or subcritical. So if you next time if you go to a flowing water body, just throw a stone and observe where the ripples are moving. If they are moving in the upstream direction, you may classify it as supercritical flow, and if you are moving in the downstream direction, it is a upstream, sorry, it is a subcritical flow, and downstream it is a supercritical flow. So that is how you can visualize the movement of flow. Okay, now let us derive the condition for maximum discharge. So the again coming back to our famous equation, that is equation 3. So E is equal to y plus q square upon 2ga square, making q as the subject. So q is equal to a under root 2g e minus y. So differentiating this equation 7 with respect to y and equating to 0, so that becomes dq by dy is equal to under root 2g e minus y into dA by dy minus ga under root 2g e minus y. Now what is dA by dy? That is t. Now from equation 7, if I take this here q by a, what is left? Under root 2g e by y. Okay, so that is what we get. So let us substitute these values back into our equation 7. sorry, above equation which we differentiated. So this becomes q by a, q by a into t minus ga upon q by a. So this is qt by a is equal to ga square by q. So that is nothing but q square t upon ga cube, that is 1. So your equation 8 represents the critical flow condition. So that again proves our point that the critical flow is a condition of minimum specific energy and the maximum discharge, as we observed earlier. So now let us understand the depth discharge curve. So here we understand the variation of discharge with depth for a fixed uh, specific energy. So the discharge would increase gradually till the point of minimum specific energy or the critical depth at which the discharge is maximum, and then again it will start reducing with the increase in depth. So at this point you can say that the flow is critical, above which the flow is subcritical, and below which the flow is supercritical. So this is a variation of discharge with depth and is called the depth discharge diagram. Now coming to the last topic, we'll understand what is specific force. Okay, so in the first lecture we discussed, when we discussed the governing equations, the momentum equation. So we had a control volume and the forces acting on the control volume. So we can have this force F1, the force F2, then there is a resisting force F3, that is a friction force, and the weight component, that is F4. So the momentum change per unit time in this control volume can be expressed as rho q into beta 2 v2 minus beta 1 v1, that is p1 minus p2 plus w sine theta minus ff. Okay, so just recalling our discussion now, for slopes of very short horizontal reach of a channel and a prismatic channel, your theta will become 0, so your w sine theta becomes 0. We neglect the effect of friction because our reach is very short, so ff is again 0. And since it is a small prismatic channel, your non-uniformity is not there, so beta 1 and beta 2 are unity. So your equation 9 now becomes rho q v2 minus v1 is equal to p1 minus p2. Now p1 and p2 are the hydrostatic pressures, so that is rho g a1 z1 bar and rho g a2 z2 bar. Now z1 and z2 are the distance of water surface to the centroid of area. So if you have this area, so from this, if this is a centroid, this will be your z1 bar distance. Now applying the continuity equation, V1 is Q by A1, your discharge is fixed, and V2 is Q by A2. So modifying this equation, that is rho Q into Q by A2 minus Q by A1, that is equal to rho G A1 Z1 minus Z1 bar minus A2 Z2 bar. Okay, now let us solve this equation. So on solving, you get q square upon GA2 plus A2Z2, that is equal to q square upon GA1 plus A1Z1 bar. So we can see that this is a, both the sides are analogous, and it can be represented by common function, that is f is equal to q square upon GA plus Z into A. So this function is a combination of two parts. The first part represents the momentum of flow that passes through a channel section in unit time per unit weight of water, and second is again force per unit weight of water. So essentially this entire term represents force per unit weight of water, and that is called specific force. So it is the force per unit weight of water. So that is the specific force. Now, so equation 11 can also be represented as F1 is equal to F2, because both the LHS and RHS terms represent specific force. So that implies that the specific force at both the sections are equal, provided that there are no external forces or weight components that are acting in between two, or they are essentially ignored. So let us understand how the covariation of the specific energy and specific curve can be interpreted. So on the left you have the specific energy curve, and the right you have the specific force curve. So This is your channel section. This is the centroid, that is Z bar, that I was talking about. So you're well known with the specific energy curve. So your Q is constant. So for a given specific energy, you have two alternate depths. So one is Y1 and this second corresponding to P2 dash, that is Y2 dash. So these are the two alternate depths. Now again, for a specific energy curve, for a given specific force, there are two depths possible, y1 and y2, and these depths are called sequent or conjugate depths. So sequent and conjugate depths imply that the depths having the same specific force. Now mind you, this charge is constant in both the cases. So this is the point of critical depth, that is C, that corresponds to the critical point C dash in a specific energy curve. So depth is yc. Now, so the depth y1 in case of specific energy and specific force curve, that corresponds to a low stage and high velocity. So that is a subcritical, supercritical region. Now the depth y2 corresponds to a high stage and low velocity. So it is in the supercritical region, and here y2 dash again it is a supercritical region. So the two curves indicate that jointly the sequent depth y2 is always less than the alternate depth y2 dash. So you can see this alternate depth y2 dash comes somewhere here and the sequent depth comes somewhere here. So the y2 is always less than y2 dash. Now why that happens? That is our question. So to be very specific about it, that since this y2 that corresponds to a specific force, now in order to maintain that y2, you can see this axis, you get another specific energy E2. So now that is different from the specific energy E1 and it is less than E1. So that implies that while maintaining that y2 depth, there is some loss of energy, that is delta E. So that loss of energy happens. Okay, so such kind of energy loss happens in case of a hydraulic jump we saw earlier. So the hydraulic jump is a phenomena where the loss of energy happens, and that is why this, to understand a hydraulic jump phenomena, you require both the energy and the force concepts. Okay, so that is, again you have to, I just given you some hints, so understand why the sequent depth is always less than the alternate depth. Lastly, we will derive the criteria for critical state for the specific force. So for the minimum value of specific force, we'll differentiate equation 12 with respect to y and equate it to 0. So df by dy, that is equal to minus q square upon ga square into dA by dy plus d by dy of z bar into a, that is equal to 0. Now this term is t. Now when we differentiate it, we get a into z plus dy plus t dy square by 2 minus a into z. Now let us ignore the higher differentials. Okay, and this a into z and minus a into z will cancel out. So what you are left with, you are left a dy by dy. So dy by dy again cancels out, so you are remaining with a. So d by dy of z into a becomes a. So substituting all that in equation 13, we get df by dy is minus q square upon ga square into t plus a. So q square t upon ga square, that is equal to a, and that ultimately is q square t upon ga cube is equal to 1. So that brings that the critical state, that is the specific force, is minimum. And lastly, if we put q by a is equal to v and a by t is equal to d, so this equation 15 is v square by 2g is equal to d by 2. So that means at critical state, your velocity head is equal to half of your hydraulic depth. So it is a very important relationship for the critical flow. So with the help of this, we understood that what is specific energy, what is specific force, and how they are related to the critical state of flow. So with this, in the next lecture, we'll go on computation of critical flow and the applications of the critical flow. So thank you very much, and we'll meet next time.